So this is what we are going to wrap up the transfer function, the system modeling with, and we are going to look at the DC motor transfer functions. So when you talk about the DC motor transfer functions, this is the DC motors are often employed in a control system where the appreciable amount of shaft power is required. And you'll find that they usually have separately excited fields, and they can either be armature controlled or field controlled. And when you talk of the armature controlled, then it means that they are either armature controlled with fixed field current, or they can be field controlled with fixed armature current. So we are going to start by looking at the transfer function of the armature controlled DC motor. So the first one, we are going to look at the transfer function, armature controlled DC motor, transfer function of armature controlled DC motor. So when you talk about this, then this is now what we are talking about as the electromechanical systems, because you'll find that the motors usually take electric current and convert it into mechanical movement. So that is why we refer to it as electromechanical system. So it has a combination of both mechanical systems and electrical systems. And in this case, you'll find that the motors, because they are always rotary, they rotate. So in that case, it is a combination of electrical systems and the rotational systems, whereby we talk of the torque, where that is the turning effect, and so on. So we are going to look at the armature controlled DC motor, and we are going to look at that with the reference to the schematic diagram that is shown here. So we can find a schematic diagram. So here we have the schematic diagram of the motor, where we have all that. That is the diagram, that is the resistor, inductor, of course the armature, and so on. So that represents the system. And when you, just as we said, when you talk of the armature controlled, then you usually have the fixed field current. In this case, you'll find that IF is a constant. So when you talk about this system, so we've talked about what each and every expression, what is represented by each and every expression. Like we've said that the RA will be the armature winding resistance in ohms, LA will be the armature winding resistance in henries, and IA is the armature winding current in amperes. It will be armature winding current in amperes. Will be the armature winding current, and that one should be in amperes. Then IF is the field current, again in amperes. EA is the applied armature voltage, and that is in volts. EB is the back EMF in volts. Theta is the angular displacement of the motor shaft in radians. And then the torque delivered by the motor in kg-m is T. J is the equivalent moment of inertia, and the load that is referred to the motor shaft, that is kg-m squared. Then we have equivalent viscous friction, that is the coefficient of the motor, and the load that is referred to the shaft, and that is kg-m stroke rad per second. So when you talk about this, then you'll find that the motor torque T that is delivered by the motor is proportional. You'll find that the motor torque that is delivered, the motor torque T that is delivered by the motor is always proportional to the armature current IA, and also the air gap flux phi, which in turn is actually proportional to the field current. And that is to say that the phi that we are talking about here is proportional to IF. The phi is proportional to IF, and phi, which means therefore we can say that phi is equals to KF-IF. Phi is equals to KF-IF, where KF is a constant, where KF is a constant of proportionality, where KF is a constant. So that is the first expression that we can talk about, where KF is a constant. So when you talk about KF in this case, that one simply means that in the first expression we did say that the torque that is delivered So in the first expression, we say that torque is directly proportional to Ia, which means T is equals to K, is proportional not to armature current and the air gap, proportional to Ia phi. And from here, we see what phi is, which means torque is actually equals to K Ia phi. And so if we now get what the torque is, and we know what phi is, then we can simply say that torque is now going to be equals to Kf Ia. You can call that one K1. It will be Kf If K1 Ia. And that is now the expression where again K1 in this case is also a constant, where K1 is also a constant. So when you talk about the armature controlled, in the armature controlled DC motor, you will find that the field current is always held constant. So anything that expresses the field current, we can also talk about that as a constant, and that one leaves us. So it means that anything that is with the field current will be a constant, and that one leaves us with the equation T. You can talk of T is equals to, and then we can combine all this. All these are now constant. We can have them to have a constant K, which is now Ia, K Ia. So T is equals to K Ia, where K is what we refer to as the torque, the motor torque constant. K is the motor torque constant, where K is the motor torque constant. K is actually the motor torque constant. We can call that one, we can have that as the expression for the torque of the motor. Then whenever the armature is rotating, then a voltage proportional to the product of the flux and the angular velocity is induced in the armature. And this one will happen if we have a constant flux. Then the induced voltage that we talk about as EB, that EB, the induced voltage EB will be such that the induced voltage EB is such that it is directly proportional to the angular velocity. It is directly proportional to the angular velocity. So EB is directly proportional to the angular velocity, the theta all over dt. So it is directly proportional to the angular velocity, the theta dt. And that is to say that now EB can be equals to a constant of proportionality. For us to remove that proportional sign, we can talk of a constant proportionality, KB d theta all over dt. So that is now what we have, and we can call this one equation number 1. We can call that one equation number 1. We can call that one equation number 1, where KB, again, we can say that the KB is a constant. So we can express this in terms of Laplace transform. So taking LTs, taking Laplace transforms. So if we take the Laplace transforms of this, then we can say EBS will be equals to KB, then ddt becomes S theta of S, becomes S theta of S, and that is now what we have in that case. And that is now, after we have that, we can now have a block diagram. So when you talk about EB, in that case, if we have the block diagram, so we are talking about EB as a back EMF. It is a back EMF. And when you talk of a motor, we know that the equation of a motor is such that V is equals to IA RA plus EB. Then from there, EB is the back EMF, whereby if EB is the back EMF, it means that at that point, the motor behaves like a generator, and therefore, the input is actually theta. So if we represent that one in a block diagram, then we can have that. Then the input is theta of S. Here we have KB. We have KB, KBS. Then the output is actually now the EB, which means we have EB of S. So that one is the first equation that we've come up with. When you go to the second one, we can now talk about the speed of the armature-controlled DC motor. And the speed of the armature-controlled DC motor is such that the speed of the armature-controlled DC motor is controlled by the armature voltage EA. And we can now, looking at the schematic diagram, we can now come up with the differential equation. So if we look at the schematic diagram that we had, then the differential equation will be such that we have LA DIA all over dt plus, then we had, that is now for the inductor, then we had RA for IA for the resistance, and that one now plus EB, which was now the back EMF, should be equal to, and that one should be equal to EA. That one is equals to EA, and this is simply to say that we can simply reorganize this and then say that maybe you can take the Laplace transform, taking LTs, taking Laplace transform, you can talk of LA ddt will become SI A of S plus RA IA of S plus is equals to EA of S minus EB of S. So that is what we have. So if we reorganize this equation, then we can simply say making IA of S, so we can have IA of S into LAS plus RA. So that is what we have, is equals to EB of S minus, not really EB, but EA of S minus EB of S, which means that we can simply say that IA of S, therefore IA of S is equals to EA of S minus EB of S all over LAS plus RA. And that is now what we have as far as that is concerned. So maybe we can talk about the differential equation here to be our equation number 2. And then this one, we can also develop its block diagram. We can develop the block diagram for the same. And if we develop the block diagram for the same, what you can see is that because from what we refer to as the Lenz's law, it is such that the EB will be opposing, and therefore we can have in control system the EB will always represent the feedback. So if we draw the block diagram, then in this case we'll have EA of S, then we have that, then here we have EB of S, then after the EB of S, then of course we have this one as the block, whereby we have 1 all over LAS, 1 all over LAS plus RA. And then the output now will be IA of S. That is now the block diagram when you look at it from the differential equation part. So that is the second part that we are going to come up with to develop the block diagram. So we can now look at now, the next thing that we are going to look at now is now the relationship between now the electrical systems and also the rotational system. So in this case, we are going to look at the relationship between the electrical systems and the rotational system. So when we look at that option, then you'll find that now the armature current usually produces a torque which is applied to the inertia and the friction. And in that case, we are now looking at, we are comparing, we have J d squared theta all over dt squared. That is now, if you look at the schematic diagram, we had the elements for the moment of inertia, and also we had the elements for the viscous friction, which now will represent the torque that will be developed by the motor. So in this case, our torque that is going to be developed by the motor will be represented by J d squared theta or over dt squared, to represent the moment of inertia, plus the viscous friction, which is F d theta all over dt. And that one should actually be equal to the torque, which is also the same as KIA that we talked about earlier. And this one, we can call it equation 3. This one, we can call it equation number 3. We can call that one equation number 3. And then we can take the Laplace transform. So taking Laplace transforms, so if we take the Laplace transforms, then what we can now get is now j, that one, s squared theta of s plus f s theta of s is equals to kia also of s. So if you look at that, then we can now develop the block diagram. The block diagram will now be, the input will be ia of s, getting into that. And then if you, maybe we can simplify the equation first before we can draw the block diagram, so that here we have theta of s into js squared plus fs. Close that is equals to kias. Then from there we can see that ia, so if we develop that, we can now have ia of s getting into that. Then here we have k all over js squared, so k all over js squared plus fs. So that is what we have as far as that is concerned, and the output now is actually theta of s. The output is theta of s. Now we have the three block diagrams, so we can simply develop the overall block diagram and then come up with the transfer function. So combining the block diagrams, we can have, if we combine the block diagrams, so we can say combining the block diagrams. So we already have 3 block diagrams that we are going to combine. Combining the block diagrams. The first one, we talked about it as being at the feedback. So if we do that, then we are going to find EA of S coming into that. So we start with that. Then here we have IA, we have EB of S. So the difference is there. Then here we have 1 all over LAS plus RA. Then here we have IA of S. Then here we join it with this K all over J S squared plus FS. Can have that one as FS. Then the output there is actually theta of S. And we can come down here, and then we have that one, KBS. Then here we have this, which is now that is now the overall block diagram. So from that, we can use now the block diagram methods in order to obtain the transfer function of the overall transfer function of this, of which now, if we use the overall block diagram in order to come up with the overall transfer function from there, then we will find that this one will multiply that, and then that one will be the feedback. Then from there, you'll find that the overall transfer function will be given by, we can talk about theta S all over. We can talk about theta S all over E of S will be equals to the product of that, which is now going to be K, which is going to be K all over. We can have S into LAJS squared, LAJS squared, plus we can have LAF plus RAJ. Then maybe can close that bracket, have S there, and have this one this way. Then there we have S. Then of course plus RAF plus RAF plus KKB plus KKB. So if you look at that, then this one will be closed in that manner, and that is now the block diagram, the transfer function of that particular system. So therefore, this one represents the transfer function of the DC motor, that is the armature controlled DC motor. That is the transfer function of the armature controlled DC motor. So in our earlier discussion, we talked about the armature controlled DC motor, and now here we are talking about the field controlled DC motor. So that is the schematic diagram. We have the RF, we have the IF, and then we have the armature side, where we have all those parameters. So the parameters are described. We have RF, we have LF, we have IF, which is the current, and so on, until you get to the F for the equivalent viscous friction of the motor, and the load that is referred to the motor shaft. So that one is what we have as far as this is concerned. So those ones are just description of what we will use in order to come up with the expression. So when you talk about this system, so in this particular system, the field current IF is actually the control input, and the armature current IA is always maintained constant, and this one may be accomplished by applying a constant voltage source to the armature and inserting a very large resistance. You insert a very large resistance in series. You insert a very large resistance in series with the armature, and if the voltage if the voltage drop in this particular resistance is large compared to with the maximum back EMF by the rotation of the armature, then the effect of the back EMF is actually made to be very, very small, and thus keeping the armature current constant. So in this case, one thing that you will notice is that in this case, the EB, the effect of the back EMF will be negligible, especially if the current, if the voltage that is added in series is very, very large enough, and therefore from there we can now start looking at the transfer function. So when you look at the transfer function of this, we are going to start by looking at the torque. So the torque T that is developed by the motor is proportional to the product of the air gap, flux, phi, and the armature current IA, so that we can say that T again is directly proportional to phi IA. T is proportional to phi IA. That is to say that T, that is equals to, that is to say that T is equals to K1. We can call K1. T is equals to K1. Then we know that we have IA, phi IA. K1 phi IA, where K1 is a constant. However, the air gap flux and the field current are proportional, and therefore for a given operating range, and therefore we can simply say that IA will be assumed to be constant. And if IA is assumed to be constant, then what that one simply means is that T will now be, we know that phi is still IF, we still phi is KF, IF. So in that case, you still have torque to be KF, IF, K1, IA. So anything to do with A will be a constant. So that one will be constant. Then what will remain is F, and therefore that one we are going to have a very big constant combining KF, K1, and IA. Therefore torque will be given. We can call it K2. We can have it to be K2 IF, and we can call that one equation 1. So that one is the equation that relates the torque and the armature and the field current, where K2 is a constant, and the equations where K2 is a constant, we can talk of K2 where K2 is a constant. Where K2 is a constant. So after that, we can now go to the equations for the systems. So we've held the armature side constant. So the equation of the system, we are going to consider the left-hand side. And if we consider the left-hand side, then we can find that, in that case, LF dIF all over dt plus LF dIF all over dt plus RF plus, so this plus RF, so IF RF plus IF RF will be equal to EF. All of that one will be equal to EF. So we are talking about EF here will be a voltage drop here plus EF here will be a voltage drop here plus that, and then from there we can find that one to be what we have, and therefore we can refer to this one as equation number 2. And refer to it as equation number 2. So we can take the Laplace transform, taking LTs, taking the Laplace transform. So if we take the Laplace transform, we can have LF, then dt will become S, I f of S plus IF of S, RF is equals to EF of S. So that is what we have. Therefore, if we look at the block diagram, so the input is EF of S and the output is IF of S. So if we look at the block diagram for that equation will be, the block diagram will be EF of S, then gets into that block. EF of S gets into that block, that is 1 over LF, 1 all over LFS plus 1 over LFS plus RF. And then we have the output there, and that is now IF. That is now IF of S. It is now IF of S. So that is the first block diagram that we are going to have. Then again, we now look at the motor torque equation, and the motor torque equation, we now look at that. We look at the elements. We have the element for theta. We have there are two elements. There is the moment of inertia, and there is the viscous friction. So if we have the two of them, then we can just come and get the differential equation for that, the integral differential equation, or relating to that, and that is to say that we can talk of J. So in that case, the moment of inertia J d squared theta all over dt squared plus F d theta all over dt should be equal to torque, which is K2 IF, which is now the equation 1. So that is what we have in that case. We can call that one equation number 3. So from there we can have K2. So we can have the block diagram for the same. So if we have the block diagram for the same, then we can talk of IF. So for that IF, before we can do that, we can take the Laplace transforms, taking LTs. J ddt will be S squared theta of S plus F S theta of S is equals to K2 IF. So that is what we have, theta of S into J S squared plus F is equals to K2 IF of S. So if we reorganize that, the block diagram will now be IF. So we have IF, then that one will multiply 1 over J, not 1 but K2 all over J S squared plus F. Then here we have the output, which is theta S. We have the output, which is theta S. So that is the second and the last block diagram for that. And therefore, we combine the two block diagrams. So we're combining the two block diagrams, combining the block diagrams to get the overall transfer function. So combining the block diagrams, we have IF, and we start with EF goes to that. Here we have 1 all over LFS plus RF, and of course the output for that is IF of S. Then it gets into that, where we have K2 all over J S squared plus F. Then we have the output theta of S. And that is now the overall block diagram, of which if you get the overall, this one suggests two blocks that are in series, and therefore you just multiply the two of them and get the expression for the system transfer function, that is theta of S all over EF of S, which is simply going to be K2. It's going to be K2 all over K2 all over. So we are going to have K2, K2 all over S. So we have LFS plus RF, then that one JS squared plus F. You can simplify it in any other way that is possible, but that one is what will give you what the transfer function is all about. So that is actually the transfer function for the generator for the field controlled DC motor. If you need more of this, more examples, you can go to EEES.education. You'll find the transfer function for the generator and so on. And that is all we can talk about as far as system modeling of electro or mechanical systems are concerned. So in our next tutorial, we are going to talk about we are going to talk about system performance. That is the steady state and also the transient response. So keep watching.